Hello everyone, my name is Quan, and today I'll be talking about our work on building behavior signatures for JavaScript in order to detect a filter list evasion. So first, let me begin with some background information on filter lists. So what are filter lists? Well, if you have ever used ad blocking browser extensions such as AdBlock Plus, you know what such extensions can do for you. So basically, it's going to block all of the advertisement and tracking related contents from a website. But behind the scenes, how do browser extensions such as AdBlock Plus know which resources to block? Well, it turns out that they rely on a set of filter lists, which are basically crowdsourced blacklists over the domains and URLs that are known to serve privacy-harming content. But such filter list-based blocking is prone to simple evasion attacks from the web trackers. So for example, one of the things the web trackers can do is to simply move their contents which are being blocked at one location and hosting them on a different location. And given the crowdsourced nature of the filter lists, it's going to take some time, if ever, for those new locations to be blocked as well. Another thing the web trackers can do is to convince the website owners to inline their content directly into the page. So in such cases, there would be no domain or URL for the filter lists to target, so it becomes impossible to block them. Finally, if the web trackers want to be really malicious, they can also merge their tracking scripts with other benign scripts that implement desirable functionalities, such as a video player for a website. So this is going to present filter list-based blocking with a lose-lose scenario of having to choose between either allowing the benign contents or allowing the privacy harm. So to summarize, it is really trivial for the web trackers to evade filter list blocking, but by comparison, it is significantly more difficult to even be able to detect when such evasions are taking place. And therefore, our goal in this work is to detect filter list evasion. And in particular, we want to focus on the executable JavaScript code because such contents have the potential to cause the most privacy harm simply by virtue of the flexibility of being able to execute arbitrary code in the user's browser. And in terms of methodology, we rely on building identifying behavior signatures of the privacy harming scripts. And then based on the signatures, we further build a tool to allow us to detect filter list evasion in the current web. But in order for us to build behavior signatures, we first need to know what the scripts are actually doing during runtime. So for this purpose, we rely on a set of browser instrumentations, which we refer to as PageGraph. So PageGraph has been implemented for the Chromium browser. And what PageGraph does is that it records the runtime actions taken by the scripts into a graph. And by script actions, we include events such as DOM interaction, web API usage, and network requests made by the scripts during runtime. So all of these are recorded into a graph that naturally extends the notion of a DOM tree, which is already maintained by the browser. So in such a graph, the nodes are going to represent the elements of a web page's environment, such as the DOM nodes, the script units, and the fetched network resources, while the edges represent the interactions among the nodes. PageGraph is an effort that's spearheaded by Brave Software, which is our collaborator for this work. And Brave has also open sourced PageGraph. And here is a sample page graph which we recorded for a web page that contains the open source fingerprint.js2 library. So next, I'm going to talk about how we generate signatures from the actions recorded by PageGraph. And to do that, I first need to refresh up on the concept of the JavaScript event loop. And this concept is a consequence of the fact that JavaScript has only a single threaded execution model. So what this means is that for a given web page, only one script on the page can execute at any given time. And whenever a script is executing, it's going to monopolize the CPU until either it finishes or otherwise voluntarily yields control. So in this arrangement, whenever a script is given a chance to execute on the CPU, we refer to this as the script being given one turn on the event loop. And therefore, in order to extract the signatures, all we have to do is to extract all the actions that happened for a script during one turn on the event loop. And if the script is given multiple event loop turns, then we will extract multiple signatures. And therefore, under this definition, an event loop signature is a subgraph of an entire page graph that will record it for a web page. And here is one such example of a page of an event loop signature, which we extracted for a canvas fingerprinting script. So in this example, we can easily see that during one turn on the event loop, the script first injected a canvas element, and then you used two web APIs to operate on the canvas element in order to derive a fingerprint for the browser. Now, we want to make the point that not all of the event loop signatures are equally important for detecting future list evasion. This is because for such purpose, we are only interested in the signatures which contain privacy-related events. And in this work, we define such events to be those that are related to either storage accesses or to making network requests. So these two types of events are important because, for example, in the case of storage events, it might be possible that the script is trying to persist a tracking ID in a user's browser, while for network events, it might be possible that the script is trying to leak privacy-sensitive information about a user to third parties. Now, in order to use our signatures to detect future list evasion, we first need to have a notion of ground truth. And for this purpose, we use the scripts which are currently blocked by EasyList and EasyPrivacy as our starting point. So basically, we're going to crawl the Alexa top 100,000 websites, and then we're going to extract all of the privacy-related event loop signatures from the EasyList, EasyPrivacy blocked scripts. But then again, we want to mention that not all of the signatures extracted in this manner will be useful for detecting future list evasion. This is because in order to reduce false positives, we have to impose a minimum size on the signature. And this is necessary because, for example, if the signature is really small, let's say containing only 2 nodes and one edge, then such signatures will not be specific, and they will end up matching a lot of unrelated scripts. So the way we determine the minimum size is to use an iterative approach. So basically, we're going to start at a very small minimum size, and then we're going to manually inspect random samples of the scripts which are matched by the signatures. And if we find a false positive during this manual inspection, then we're going to increase the minimum size and then try the whole process again. So in the end, we arrived at a final minimum size of 13 edges and 4 nodes. Now for evaluation, as I mentioned, we applied our system to crawling the Alexa top 100,000 websites. So from the scripts which were encountered during this crawl, we generated close to 2 million instances of privacy-related event loop signatures. And from these 2 million, about 400,000 of them are unique. So this number is smaller because a lot of the scripts are included on multiple websites, and they all end up generating the same signatures. We also found that the average number of privacy-related signatures per website is 22.7, and the average number of privacy-related signatures per script is 2.54. So next, we want to use the signatures to detect future list evasion. So the first thing we did was to see how many of the 400,000 unique signatures, as we mentioned, are generated from EasyList, EasyPrivacy blocked scripts. So in total, there are about 5,500 such unique signatures. And from these 5,500, about 2,000 of them have the required minimum size, which, as you recall, is 13 edges and 4 nodes. So we will refer to these 2000 as our ground truth signatures. And these are what we'll be using to detect filter list evasion. The rest of the 3500 do not have the required minimum size, so we refer to these as the small signature set, and we discard them, meaning we do not use them to detect filter list evasion. In the table here, we show statistics for the scripts which are matched by the signatures in both of the two sets I just mentioned. So as you can see here, our ground truth signatures matched a total of 14.8 thousand unique scripts. And of these 14.8 thousand, 11.2 thousand of them are blocked by easy list and easy privacy. But we also found about 3,000 unique external scripts, as well as 500 inline scripts that exhibit the same privacy harming behaviors as those blocked by easy list and easy privacy, but currently they evade filter list blocking. So in total, we found about 3,600 unique evading scripts. In the table here, for comparison, we also show the corresponding numbers for the small signature set. So the point here is to show that they ended up matching much more scripts. And this confirms that they are indeed less specific and therefore more likely to introduce false positives. And next, we're interested in classifying each one of the 3,600 unique evading scripts, which we found in a previous step, based on the method that they employ to evade filter list blocking. So for this taxonomy, we came up with 4 categories in total. And in the table here, we show the categories as well as the number of unique scripts out of the 3,600 for each one of the categories. So the first 3 categories shown here are actually based on the evasion techniques, which I mentioned earlier in this talk. So the way we classified cases for each one of the categories is by comparing the AST structure of an evading script against the scripts which are blocked by easy list and easy privacy. And also out of the 720 cases in the moving code category, we also submitted 586 filter list rules based on the script's URLs to easy list and easy privacy, so that those scripts are now also being blocked at their new locations. The last category in our taxonomy is the common code category. And this is intended to be a catch-all category for the cases which do not fit in the previous 3 categories. So one of the interesting things we found for the cases here is that a lot of them are actually tracking libraries which are never intended to be used by themselves, but are instead included as dependencies by other tracking scripts. We also found that a lot of the scripts in this category share a significant portion of the AST with an easy list, easy privacy block script. So in total, there are about 2,300 cases in this category. Now, one caveat we want to mention here is that it is difficult for us to automatically verify whether all of the cases in this category are true positives or not, simply due to the complexity of the JavaScript code that is involved. But we also want to mention that the false positive rate is likely very low, because during one of our manual inspections of more than 100 random samples from this category, we found only 1 false positive case. Lastly, to conclude this talk, I would like to mention some of the directions for future work. So in this regard, one of the first things we can try to do is to improve the granularity of the actions that are captured by PageGraph. And in particular, we want to be able to cover more of the web API access events. And when this is done, we can also improve the granularity of our signatures so that they become more specific, and therefore we can reduce the false positive rates even further. Another thing we can do here is to investigate applying the signature-based detection method described in this work to real-time blocking of known privacy-harming behaviors from the scripts. So ideally, such mechanisms should run directly inside the user's browser so that their privacy is protected as they visit the web. Thank you for your attention, and I hope to see you at the conference.